So, good afternoon. Let us discuss the next topic, which is the vertical stresses in soils. But before that, I have to be honest with you. I'll do this time recording or siguro sa sunod na to nga mga topics mag-recording lang ko because dili na ako matansya ang akong schedule due to my work. I have my administrative load, which is the project implementing unit. I am inspector of the different projects here in the university. So, usahay, dili ko makamit sa inyo due to my schedule. But I will do my best, try my best to have this recorded lecture. So, please bear with me, and please watch and study the lecture notes and the videos that I posted, and also this one, this recorded lecture. So let's proceed. We have the topic outline, the stresses in soil mass. So we'll discuss the stress in soil mass, stress due to concentrated load, the Boussinesq method, simplified method, approximate method, and stress due to embankment load. For the intended learning outcomes, explain the stress distribution in soil mass when subject to foundation load, calculated the estimated net stress increase due to foundation load. So first is we'll understand the stresses in soil mass due to external load. So the stress in soil mass when soil is subjected to vertical load such as foundation, stresses are created in the soil. Of course, so we have here a drawing of the, if this is your footing, of course, naa siya nag-stand na siya sa soil. So, this load here sa imong building will create stress in the soil. So, how to calculate the stress in the soil? The stress is spread laterally in depth, with depth. As you go deeper, the stress decreases but affects a larger plan area. So, remember that the unit of the stress, or that is the pressure, is actually P, the force over area. So, like this one, if you try to kuha na siya, that will look like that one. The behavior of the stress, So, as you go deeper, kung magkalalom ka dire, meaning the area will be bigger, yapon. So, the force, if there is like the concentrated force P, then in here or immediately in here, kaning sa interface between the footing and the soil, the pressure or the stress is maximum. But as you go deeper, since the area will be bigger, you have here the ratio, so magkadako ang area diri nga part sa magkalalom, so meaning the stress will be smaller, So as you go deeper, the stress decreases but affects a larger plan area. For example, if 5 feet by 5 feet footing at z is equal to 0, meaning the immediate interface, between the footing and the soil exerts a stress of 2,000 pounds per foot square per square foot over a 5 feet by 5 feet area. But at z is equal to 5 feet, or meaning, for example, if this is your footing, then 5 feet, for example, kani diri dapit, this is 5 feet. The stress is maybe half na lang, So, from 2,000, nahimo siyang half at z is equal to 5 feet, but over an area of 10 feet by 10, feet because nidako naman imong area diri. This part here. So that is why as you go deeper, the stress decreases. Numbers only an example, actual calculated stress will be different. So in simpler terms, load P over area results in stress Q with depth. P stays the same, area increases, no? Like this figure, and Q or the stress decreases. So if this is the footing, you have here the load P. Of course, the stress is P over A. So as A increases, P stays the same, Q decreases, no? So this will be your considered area na if at Z distance, no? What is this? Z distance, no? From here, footing to here, no? Importance of stresses in soil due to external loads, prediction of settlements of the buildings, bridges, embankments, and bearing capacity of soils, and also for lateral pressure. So that is why it is very important now to determine the stresses or the bearing capacity, yes, the stresses in soil due to external loads. So these are the kung unsay gamit, no, sa stresses in soil, unsay gamit nung kailangan mahibal-an ang stresses in soil. Theory of theory of elasticity in engineering mechanics, strain is the ratio of deformation to length, no, and has nothing to do with working out. In an elastic material such as steel, strain is proportional to stress, which is why spring scales work. Soil is not an ideal elastic material, but a nearly linear stress-strain relationship exists with limited loading conditions. Ba? A simplification, therefore, is made that under these conditions, soil can be treated mathematically during vertical compression as an elastic material. The same assumption frequently is made in finite element analysis. So soil can be considered as the elastic material but at a certain loading conditions lang siya. So it will behave actually the same material sa mechanics na stress-strain relationship, no? But lagi as indicated here, limited loading conditions. Soil is considered quasi-elastic or is described as exhibiting near linear elastic behavior. There is a limit to near linear elastic behavior of soils as loading increases and shearing or slipping between individual soil particles increases. So sa engineering mechanics, remember that the Hooke's law, di ba? Or the proportional limit. If this is the stress and this is the strain, this part here, this is actually the proportional limit. Dayon, at some point, this is the behavior actually of steel, di ba? At some point, according to this statement here, theory of elasticity in soil, soil is considered as quasi-elastic or near linear elastic behavior. So actually, behave gihapon ang soil ani, but at a certain loading condition. So naay limit sa stress sa load, no? When that happens, any semblance to an elastic response is lost as shearing more closely simulates plastic behavior. So, maduol siya sa plastic nga behavior, there is a loss of elastic response, so meaning dili na siya mo behave aning the same as sa proportional limit or Hooke's law. So this is the behavioral mode of soils in landslides, bearing capacity failures, and behind most retaining walls. As loading is, loading is increased, no? It will behave as plastic na siya, meaning that as load is increased more, or even wala ni increase ang load, tendency ana is ang imuhang deformation is big. Now that will cause landslide, or shearing failure is big, and that will cause failure or landslide sa soil. The extent of the elastic layer below the surface loadings may be any of the following: infinite in the vertical and horizontal directions, limited thickness in the vertical direction underlain with a rough rigid base such as rocky bed. The loads at the surface may act on flexible or rigid footings. The stress conditions in the elastic layer below vary according to the rigidity of the footings and the thickness of the elastic layer. So all the external loads considered are vertical loads only, as the vertical loads are of practical importance for computing settlements of foundations. So in here, we have to understand the stresses, no, vertical loads only, because it is of practical importance, no, for the settlements of foundations. So we'll only consider vertical loads, not the lateral loadings. We have this method or a procedure, no, to determine the stresses in soil mass. We have the Bosines case. Now, Bosines developed an equation to model stress distribution with depth for a homogeneous isotropic material, modulus of elasticity, and Poisson's ratio constant in all directions. Remember, for Bosines case, the soil is homogeneous or isotropic material, no? Meaning the modulus of elasticity E and the Poisson's ratio is constant, no, in all directions. For point load Q, stress at A, at depth Z, and lateral distance R from Q is, we denote as change in vertical stress, or that is change delta sigma sub V is equal to Q, that is the vertical load, over Z squared at a certain distance now from the load, or for example we have from the footing, times 3 over 2 pi times the quantity 1 plus R over Z. R is the radius. So from the point load, you can ani to certain distance to another point, no? That is the radius, meaning this is the radius over Z, the depth squared to the power of 5 over 2. So the maximum value of the vertical stress is when R is at 0, or in this point, now directly below the point load. Yes. So this one. Now the load is a point load acting on the surface. Vertical stress, or sigma sub Z at point P under point load, is given as, actually this is the same as the previous formula, no? And here the I sub B is equal to tanawa, kung tanaw nimo gisimplify niya as equal to I sub B. This one, nahimo siya, actually pareha ni siya ganina. This is the same with in here, no? Pareha na siya. Where R is the horizontal distance between an arbitrary point below the surface and the vertical axis through the point load Q. Z is the vertical depth of the point P from the surface. I sub B is the Boussinesq stress coefficient equal to this one. This. So, kung inyong tanawon, this will be simplified as this. IB. Q over Z squared times IB. Where IB is 3 over 2 pi times 1 over the quantity 1 plus R over Z squared to the power of 5 halves. So the value of the Boussinesq coefficient I sub B can be determined for a number of values R over Z. The variation of the Boussinesq stress coefficient or the I sub B with R over Z in a graphical form is given in figure. So, this one, no? So, the variation of I sub B, kani siya, no, with R over Z is malahi gyud, no? Using this representation, no? So, the Z is the distance from the load to the directly below the point load, and R is the lateral distance now from the directly from point load to a certain point. If you consider what is the stress at point P. So, ay nga na siya pag solve. We have here an example. A concentrated load 1000 kN is applied at the ground surface. Compute the vertical pressure at a depth of 4 meters below the load, meaning directly below the load, meaning your Z is equal to 4 and your R is 0. And for number 2, at a distance of 3 meters at the same depth, use Boussinesq equation, meaning for number 2, your Z is still 4 meters, but your R is 3 meters, no? So for the solution of this one, we have here the formula for the Boussinesq equation, no? Boussinesq equation, this one, where your I sub B is equal to 3 over 2 pi over 1 plus R over Z squared 5 over 2. So for number 1, no, or I, when R over Z is equal to 0, because your R for number 1 is, the condition here is at depth of 4 meters below the load, meaning your Z is equal to 4. This is the distance from the point load to below distance now directly from the point load, and your R is the radius. So meaning your R over Z is 0. And sorry. And your I sub B, using the formula, now this one is actually equal to, ulangan ni siya, that is 1 plus R over Z squared to the power of 5 halves. So using the Boussinesq coefficient, this one, the answer is, your I sub B is 0.48. And again, this equation, so 0.48 times the point load divided by Z squared is equal to 0.48. What is the point load in the problem? Equal to 1,000 kilo Newton. So, munang times 1,000 divided by Z. Your Z is 4. since this is squared, this mo ng 4 times 4. So the answer is 30 kilonewton per meter squared. The representation of that is, if you have the soil here, then you have the point load Q. What is the pressure at 4 meters? No? This is your Z. Now, this is 4 meters. This is for I condition. For double I condition, your R is 3 meters at distance 3 meters at the same depth. So, for double I condition, what is the pressure at this point? This is 3 meters. So, for single I, this is your P. What is the pressure or the stress at this point? Then, for double I, what is the pressure at this point here? No? Using the Boussinesq equation. So, when R over Z is equal to 3 over 4, this is given, no? The answer is 0.75. So, using the Boussinesq equation, the same equation, this one, the answer for R sub B, I sub B is 0.156. And the stress is equal to this, no? Kani siya. This one. This is I sub B Q over Z squared, no? And the answer is 9.8 kilonewton per meter square. So, notice that at directly below the point load, mas dako siya kaysa katong at a certain distance from the point load, which is 3 meters. Reduce siya into 9.8 kilonewton per meter square. For the continuation, a point load is never encountered in practice, no? So, the example is actually a point load. So, the Boussinesq equation for a point load must be converted to a load over an area, no? Because, as stated here, point load is never encountered in practice. But Boussinesq equation can also be used, no? Kung imuhang load is in isolated footing, perimeter footing, or slab, no? And how would this be done? This has already been done and put in tabular form for different shape foundation. So, as you noticed last week, I posted the book of the textbook, no, by Brahadas, the principle of geotechnical engineering. So, the table 9-7 is actually na-added to, no? Shows the results for the rectangular footing using the following. So, we have the M is equal to B over Z. B is always the short dimension. So, in the footing, so if this is your footing, sorry for the hiwi na kuan, but never mind the hiwi. If this is your footing, this is side view. Kung imong tanawon siya, sa kuan, say this is the top view, no, of the footing. So, B is always your smaller side or small dimension, short dimension, and L is your longer dimension. So, this is the interface nga mo touch sa soil, no? This one. So, na siya. Then, plot N and M to obtain the coefficient I sub 3. I sub 3 times the footing pressure is the stress beneath the corner of the footing. So, corner of the footing. I sub 3 times the footing pressure, no? This times is the stress beneath the corner of the footing. So, let us try to find, no, the table. I think ato sa pangitaon. Ito siya. Table dash 9.7. Yes, this one. So this is what I'm talking about kanina. So first is you have to determine your B, the shorter dimension, and L, the long dimension. Now divided by Z, which is the depth of the kuan, ang kalalom sa considered nimo nga location, no? Then plot N and M to obtain the I sub 3. Then I sub 3 times the footing pressure is the stress beneath the corner of the footing. So in here, this is N and this is M. Yes. So let's have an example later now to better understand this one saan paggamit. We have also the table 9-8. This is the same but under the center of rectangular footing. So again, you have to determine your B and your L. B is always the short dimension and L is always the long dimension. So determine the M1, which is equal to L over B, and N1 is Z over small b. While where the small b is equal to big B over 2, no? Then plot N1 and M1 to obtain I sub 4. Then I sub 4 times the footing pressure is the stress beneath the center of the footing. So this I sub 4 is for the center of the footing, no? We have here an example now to better understand the table. Example is a load of 125,000 pounds is placed on a footing. The footing is 5 feet by 5 feet. Find the stress below the center of the footing at Z is equal to 5 feet. No? First is yes, we have to determine the Q. Q is the stress beneath the corner of the footing. No? Pasabot aning. This is small q. We have to find that one by dividing the concentrated load with the area, footing area. So mo nang we have the stress 5,000 pounds per square foot, but we have to multiply this one with the coefficient. No, mo nang kailangan nato siya mo nang I sub 3 on I sub 4. The representation of that is since we have to find the stress no below the center of the footing, so we have to use the I sub 4 instead of I sub 3 because I sub 4 is for center of the footing. The representation of that is you have here the footing. Yan lang. Okay, footing. This is 5 feet by 5 feet and you have the concentrated load which is equal to 125,000 pounds, no? So the small q is equal to the stress right after the footing or the interface between the footing and the soil, no? So naamang kay kuan diri. So manang q is equal to 125,000 divided by 5 feet by 5 feet. So that is the small q, but we have to multiply this one with I for or the coefficient, Boussinesq coefficient, because we are asked to determine the stress below the center of the footing at Z is equal to 5 feet. So that is why we have to use this condition, no, for I4. Then your L is since 5 feet by 5 feet man, so meaning kung imong tan-awa na siya, this is 5 feet by 5 feet. This is your B, this is your L. So manang B, L over B for M1 is equal to 5 over 5, which is 1, and for the small b is equal to the big B divided by 2, or 2.5, and N1 is Z, which is given the depth, no, 5 feet divided by 2.5 or 2. Then using table 9.8 says that your I4 is 0.336. So tanaw na to kung sakto ba. Remember your M1 here, no, 9.8 dire. This is your M1, this is your N1. Remember your N1 is, ilagay ito, your N1 is, M1 is, I think, 1. Your N1 is, I'm not sure, that is 2. Your N1 is 2, no? Your N1 is 2. So, kung imong tan-awon, your M1 is 1, and your N2 is 2. So, this one, no? So, your I4 is equal to 0.336. This is your coefficient, no? Looseness coefficient. So, munang from here, your small q, this is your I4 times the small q. So that the stress below the center of the footing is 1,680 pounds per square foot. For I4, no? Stresses in soil mass. If you need this stress under a rectangular footing, but you need it at a point other than the corner or center, you would use the superposition. By creating a series of rectangular shapes in the area needed, you can sum the calculated stress to obtain the total stress at that point. Now, for example, we are asked to determine, okay, let's have an example, no? For example, this one, no? Okay. By breaking the larger rectangle into 4 smaller ones, you can find the stress under point A prime, which is not under the center of the corner or corner of the larger area, but under the corner of each of the smaller areas. For example, now this is the footing. Then we are asked to determine what is the stress at point A prime. No? Kani siya. Pero dili siya sa center nor sa corner, no? So ang atong buhaton is we have to divide this big area into smaller areas. Ang A prime is ma-corner siya. So pag mahitabo na siya, ma-corner na siya, meaning you have to use the I3. Because I3, the coefficient I3 is 4. Corner of the footing, no? Corner of the footing. So, nga na ang mahitabo. We have here an example, no? Find the stress in vertical stress, increase. Find the increase in vertical stress due to the loaded area at a point 5 feet below P. So, we have here a footing, no? And we have this small q. So, atong buhaton na lang ani, we have to multiply this one with the coefficient, no? But below, we are asked to determine the vertical stress due to loaded area at 0.5 feet below P. So, where is B? Nara diri ang B. So, meaning, what we are going to do is, ay, distance nga 2 feet, no? From here to here, 2 feet siya. So, atong buhaton is that we have to use, by using two areas, we can find the stress 5 feet below B. Even if ang B naa siya sa gawas, so we can still find by getting the I3 of the big area minus kani siya, kani nga area hangtod ani. Minus or subtracting the I3 of the small area. This one. Kani. I3 of the small area. Small area. So, solve by finding the change in stress for the 6 feet by 3 feet, no? Kani siya. Area and subtracting of the stress for kani nga area. No? Na siya. So, to do that one, solve for M, no? So, B is 3 divided by Z, which is 5, so 0.6, and N is 6 divided by the depth Z, 5, 1.2. Then, using the table 9.7, 0.6, and 0.2, dito ta sa 9.7, no? Remember, M is 0.6 and your N is 1.2, no? So, mo ni siyang your I3 is 0.1431. Yes, 0.1431. And the small area na pud ka. Pangitaon nimo ang kaning sa small area. Your M here is always the short dimension, so 2. I mean your B is 2 divided by the at depth, no, 5 feet. So that is 0.4, and your N is 3 divided by at depth 5, that is 0.6. Then, pangitaon na to sa table, 9.7, 0.4, and 0.6, no? 0.4 and 0.6. This is the I3 of the small area, 0.0801. So, to determine the change of the stress is equal to, this is actually the Q, small q, times the I3 of the big area minus the I3 of the small area to be subtracted na. This is your answer. So, naitabo is, gidrawing nimo ni siya, since this is corner, i-consider nimo as this big area here, ni siya. Kani. So, nahimo ni siya as 6. This distance here is 6. Minus this area. Kani. No? Because we are asked to determine what is the change of stress, no? At 5 feet below B. So, ingana siya. To use superposition, all shapes must share the point in question under one of their corners. Solve for the next class. So, this is another example, no? But, yes. Kindly solve this one, no? Solve in practice. Solve by yourself, no? Solve by yourself. So, how to compute, no? Find the stress at A. Where is A, dire? At Z is equal to 5 feet, no? So, saan man na siya ninyo? So, that is your, for you to find out, no? We have here a 2-by-1 method, 2:1 method. This method approximates stresses due to a foundation by assuming the load spreads at a rate of 2 vertical to 1 horizontal. So we have the load P and area B times B, no? This area here. So, syempre, the stress, no, at this point or at this interface, no, immediate between the footing and the soil is P over A, diba? Then, using the 2:1 method, so you have here the vertical 2 and the horizontal 1. As A increases, P stays the same, then D decreases. For square footing, B times B, the change in stress is equal to Q. This is the point load divided by B plus Z square, no? Kung square, footing, diba? And for rectangular footing, B times W, so meaning dili pareha ang dimension, no, sa base of width. So the change in stress is equal to the concentrated load divided by B plus Z times W plus Z. No, kung dili pareha. Ang nahitabuan na if is because if this is Z, nganong plus Z? Because if this is Z, then using the 2:1 footing, meaning this distance here, this will be 1/2 of Z. Also, if this is Z, this is also 1/2 of Z. And at a certain distance from the footing from here, say Z. So the area, this one is B plus this one, kani siya nga area. This is actually equal to B plus Z. Okay, 1/2 Z plus 1/2 Z is equal to 1Z, di ba? And kung square footing, B plus Z lang, squared. Pero kung rectangular footing, meaning different dimension, manang B plus Z times W plus Z. 2:1 method. Alright. Plotting change in vertical stress versus depth. So, this is actually the behavior, no, of the change of stress, vertical stress with depth. So, as you can see, magkalalum, no? Magkagamay ang stress. If this is 0 here, this point is 0, then 1, 2, 3, 4, if this is the footing depth, no? Footing depth na siya. So, magkalalom, magkagamay ang stress. Yes. So, ang nahitabo, no? Magkagamay ang stress. Yung magkaduol ng dako ang stress. This part here. Muna ingani ang ihang graph. And proceed ta na. Assume there is a footing at z is equal to 0. So actually the same concept naman tong ganina. This is explained. Also assume bearing pressure 2,000 pounds per square feet. Then the change in stress, vertical stress is 2,000 pounds per square feet. Using either Business or 2:1 method, plot stress versus depth. Now assume a layer of field placed on this. The behavior is still the same, no? The graph, no? So kung magkalayo ka, magkagamay po ang imong stress. So, no? Sakto kay because magkalayo ka dire. Remember, nara dire imong stress. Didapit. No, if this is your z is equal to 0, this part here. So, magkalong ka dire. Gamay kayo ang stress. Pero magkaduol ka, mo nang dako ang stress, this portion. Conceptually, it is like placing a 100 feet by 100 feet footing on a 100 feet by 100 feet site. Looking at the plot, what does this mean? No? What is the stress at actually maura ni siya, no? Concept actually. Iya lang di padako. I mean, iyang gi-elaborate, no, using the different depth, 5 feet, 10 feet, and 20 feet. But the same explanation ra kanina. We have another formula, no, the Westergaard's formula for point loads. The actual soil is neither isotropic nor homogeneous, no. Westergaard, the British scientist, proposed in 1938 a formula for the computation of the vertical stress sigma sub z by a point load q at the surface as this one, no? Si Business manggod siya, he considers the soil as isotropic or homogeneous. But Westergaard formulated another formula, no, because he believed that the soil is neither isotropic nor homogeneous. So, dili siya isotropic, nor homogeneous. That's why he proposes EU, which is the Poisson's ratio, no? And if U is taken as 0 for all practical purposes, then this will reduce into this one. But Westergaard proposes the equation as this, no? Using U in the formula. Kani. Because soil is neither isotropic nor homogeneous, di ba? Right. Then if U is taken as 0 for all practical purposes, then this will reduce to this one. Q sub Z is no? So makita ninyo ang kalahian sa Business equation, and where I sub W is this one, no? It is called the Westergaard stress coefficient. Si kuan pod Business equation, Business equation siya I sub B, remember ganina ang Business equation. This time the Westergaard stress coefficient na siya I sub W, no, in this formula. So the variation of I sub B, I think this is I sub B, or the Business coefficient with the ratios of R over Z is shown graphically on the next slide along the Business coefficient I sub B. The value of the Westergaard stress coefficient at R over Z is equal to 0, is 0.32, which is less, at R over Z is equal to 0 is 0.32, which is less than that of I sub B by 33%. But the geotechnical engineers prefer to use the Business equation solution, as this gives conservative results. So the geotechnical engineers prefer to use the Business equation because of the conservative results. So dagko ang mahatag ni Business equation. So this is the difference, no, of the value of I sub B, the Business equation, and the the Business coefficient and the Westergaard coefficient, no, for use in the Business or Westergaard formula. Alright. So as you can see, dagko ang ma-create, no, or ma-result sa I sub B or Business coefficient than the Westergaard coefficient with the different value of R over Z. Alright. So I think this is the problem. Then umanon lang nato ni no until the sa have here the problem